Okay, all right, good afternoon, everyone. Thank you for coming for the cold weather. I know it's a bit cold these days. It's unusual for Florida, especially. They have snow in the up north, so hopefully we can get back to the sunshine state really soon. Okay, so before we start the class, I have a few announcements. One is the project sign-up sheet. I sent out an announcement, have the Google Sheet. So you guys can, if you want to find a partner, of course you guys have to maybe discuss after the class, sending emails, find maybe your friend if you want to team up to figure out a project. Then you can sign up here. So basically put the name and also the email address so that later you guys can, within the team, you can communicate with each other, right? The second, please do that, so that help me to figure out, right, eventually how many teams are going to be there, right? Because later we'll have these project presentation at the end of the semester. The second is the GPU computing account. So there's something wrong. Okay. So the GPU account, so if you need one, send an email to TA. So we have the account requested for the ARCC, so the GPU cluster. So the TA will send you the account and some of the credentials for the login. Okay, so you can starting to think about those project and also the programming assignment. Okay, it's always good to start early. Okay. All right, so those are the two announcements. If you have any questions, let me know. For today's lecture, we'll basically give you guys a very quick like a crash course about deep learning. So if you don't have any background, then maybe these a couple of lectures will help you to get some of the basics of deep learning, because later we'll extensively talk about some of the advanced topic in the deep learning. Okay. Okay, so here is a figure just basically shows you, right? So we have the broader concept of artificial intelligence, right? Not just machine learning, but we also have other, because as a human, right, we have different senses, right? So towards the general artificial intelligence, then basically mimic how human intelligence will behave, right? So under that, we have the general machine learning. That including the classic machine learning, right, before the deep learning era. So we have the classical machine learning, a lot of very good algorithm like supported vector machines, random forest, all these classic machine learning technique, but still being used even in the deep learning era, right? So a lot of industries, right, maybe these classic machine learning technique is already enough to achieve the performance, right? So then even a narrow scope is the deep learning, right? So basically just using the deep neural network, right, to perform various tasks, okay? So because of this is a very thriving area, so basically all these different areas, we are using the deep neural network to perform tasks because we have a lot of data and also a lot of new network architectures and prove to be very successful. So there's a couple of reasons, right, why deep learning is really take off and thrive in the past decade. So there's some main reasons, right? So one is the big data, right? So we have a lot of data at our disposal, right? So for example, we have images, text, videos, right? All kinds of other type of data. Especially, if we talk about images, right? So for image classification, then we have this larger scale ImageNet data set, right? So collected from the internet. And essentially you can crawl all these internet data, right? So now, we talk about these kind of large foundation model, right? So we can essentially take all these data from the internet. Eventually will be, lack of training data, right? So where this new data come from? Because we've kind of exhausted or used all the data from the internet, right? The second, factor is the hardware, right? So before the GPU, being very commonly used, then we only have CPUs, right? So that is not very good at doing this kind of matrix multiplication, but with the GPUs, right, the highly, parallel, right, so we can do these matrix operations fairly efficiently, right, so that's a big reason, right, so we are still, advance these hardware because right now the network is getting bigger and bigger, right, we have billions, trillions of parameters, right, how can we train these models? We need a lot of compute. With a lot of data, we also need a lot of compute. And finally is the software, or more like a general community, right? So first of all is we have all these different deep learning frameworks, right? The TensorFlow, PyTorch, before we have these Caffe, but I think right now mostly people are using PyTorch and the TensorFlow, right? So these are well-maintained software frameworks, right? You can easily call some functions, and you don't have to implement, gradient descent, atom, all these optimizers, right? So you can just quickly call a function optimizer, then you can build up your own network and train the network, right? And not just these frameworks, but we also have these open source, right? We have the GitHub repo. So that really helps this community really, try not to avoid, basically avoid reinventing the wheel, right? So because if you have the open source code, then people can easily take the code, right, reproduce the result, or maybe make some modification, trying to do some improvement, right? So that can really reduce the time cycle, right? So we can focus on the most important things, trying to push this technology forward, right? So that's some of the, a couple of reasons, right? So why we are able to see how this field is going to evolve so quickly. Next, starting with the basic convolutional neural network. I know right now we are, most of the tasks we are looking at, transformer architectures, right? For the NLP or vision transformer, for the vision or image video processing, but it's all started with these convolutional neural networks, specifically, widely used in image processing and computer vision. And still, there's a lot of applications we are still using the CNN as the backbone. Okay, so we'll take a look at the CNN first. So this is the kind of like a very basic, structure of the whole CNN framework, right, or architecture. So you will have an input, right? So here we are focused on image processing, right? Computer vision. So here, let's say we have very simple task, which is doing image classification. Then you will have an input image. Then you go through some basic building blocks, right? Just like you are building like a Lego, right? So you have some basic building blocks, okay? So what are these basic building blocks? So fundamentally, we have these convolution operation, right? And we also have the max pooling, and then you also have this flattened layer, then also have these fully connected feed-forward network. So of course, these convolution and the pooling layer are consider these basic building blocks, right? You can repeat these layers a couple of times. You can scale up your network, right, to build a very deep convolutional neural network. So the first, there's a couple of properties for the CNN, right? So the first is, or maybe some properties for the natural images per se, okay? So the first property is some patterns are much smaller than the whole images, right? So for example, if I have a bird image, right? So I have a beak, right? So then that the beak of the bird is very distinctive, right? So that's maybe the key features to distinguish bird from other species, right? So, but that pattern is much smaller than the whole image, right? And also, like for this cat image as an example, right? So maybe the mouth region, right? The whiskers, all these things, maybe also a very key distinctive features. But compared to the whole image, that occupy a small region, right? And there's also some properties for the images, right? So we have same patterns could appear in different regions, right? So for example, the fur, the patterns, right? Maybe the stripes maybe occur, at different locations, right? Another maybe more prominent is, let's think about like a zebra image, right? So the black and white stripes, occur multiple times, right, across the entire image. So the same patterns will appear in different regions. And another property is if we subsample the pixels, right, so if we downsample this image, right, to a smaller resolution, that wouldn't change the object in this image, right? So if this is a cat image, if I downsample to half of the size or quarter, still this cat will remain the same, right? So the first two properties actually kind of inspire the convolution operation, right? Because we don't need a very large kernel to operate on the entire images, right? So we can have a small kernel, convolutional kernel, to kind of scan through the entire image. And the third property, right, so which can inspire us to using the max pooling or average pooling or any other pooling technique, trying to reduce the image resolution, right? So because if you keep using the same high resolution, then the convolution is basically you are doing matrix, element-wise multiplications and also additions, right? So there's a lot of computation involved. But if we can gradually reduce the size, the feature maps, right, the number of operations can be reduced. That can make the training or the computation resource much more efficient. So let's first look at the convolution operation, right? So that's the very basic operations in the CNN. So here I'm using a very simple example. Okay, so I only have a 6x6, like a grayscale, right? Not even RGB 3 channel. So consider a single channel, grayscale image, right? 6x6, and has these very, simple patterns, right? Only have 0 and 1s, right? Basically indicating a couple of, edges with different orientations, right? So here we'll apply some sort of filters or kernels, right? So basically, we want to using these different kernels to detect if some of the patterns will exist in these images, right? So, and these filters or kernels will be the network parameters later will be learned, right? So of course, before the network is being trained, we can randomly initialize these filters, right? So we have to start somewhere, right? So we can just do some random initialization or maybe some specialized initialization. So here, this example, the filter size or the kernel size is 3x3, right? So it's basically detect a small 3x3 pattern. And this is how these convolution, works. So first, we'll position this filter, right, in the first location. Then, yes.
I was going to say, just to make sure I'm following the terminology correctly. When you say kernel, can you define specifically what that is?
So the kernel is basically just like a filter. Or you can say this is like a feature detector, right? So this is just So basically, this is a convolutional filter, right? Or basically, just a matrix, okay? Mathematically, just a matrix. And these actually are the parameters we want to learn, right? So ultimately, right, once your network is trained, you will learn a very good set of filters, right? That is able to detect or extract those useful informations later for the, classification, segmentation, or object detection, right? So initially, we don't know, right, what are the right parameters to use in the filters. So we just do the random initialization. Then through the course of optimization, these numbers will change. Eventually, we'll reach a very good set of filters to detect those patterns. Yeah, this is just different names, right? You can say this is type of filter, right? Filter or extract some information. Or this is, just for like image processing, right? Signal processing, this is look like a kernel. So that's usually the terminology works, okay? All right, so here we have the first position. We'll just overlay this filter or kernel on this image position. Then we will do the element-wise multiplication, right? So this is a 3x3 matrix. The filter is also a 3x3 matrix, right? So we just do the element-wise multiplication. So you can easily see that, right? So we only have these three positions has a 1. The other will be 0, right? So in this case, we have these three positions, and we sum up them together, right? So we end up with a one value, okay? We do the element-wise multiplication and do the summation. So then the first position we get is 3. And if we're using a stride, right? So the stride means how much overlap you will shift your filter or your kernel, right? So here we just move one column to the right, and we repeat the same process, okay? Then we get another value, right? So we get a -1 here, and here if we're using a stride equals to 2, right? So which means we move 2 columns, right? So here the first position we located here, then we move two columns, then become here, right? So then you will basically just do the same process and get another value, okay? So this stride, if you don't do any padding, it will also kind of reduce the feature map size, okay? So if we set the stride as 1, right? So you just move one column at a time, then we can basically scan across the entire image, right? So just think about everyone used a flashlight before, right? So of course the flashlight is a circular. If you put that flashlight onto a wall, the visible area or the light area is like a circle, right? But just imagine, you have a square, flashlight, right? So the imaging area is like a square. So that can be your filter, right? So then you can think about, you just kind of scan through the entire image, right? So how these light area move around this image and to get all these resulting value, okay? So that's the last one. So because we don't do any of the padding, right? So we end up have a reduced feature map or resulting a reduced image size, okay? So one thing you can look at here is for this specific filter, right? So we are kind of, because the nature of this filter, right? So we are basically trying to detect like a diagonal edge, right? So if we look at this, right? So we actually able to detect such edge, right? So we have ones on the off diagonal. Here we are able to generate a large response, right? So we are able to detect similar patterns in this image. So this is another one, right? So if we have ones on the diagonal, so this type of filter is able to detect these kind of patterns, pick up, generate a large response in this corresponding area, right? Okay. So then, of course, we don't have to just using a single filter, right? Because images are very complex. There's very diverse features we want to extract and maybe later use them, right, to do some high-level tasks like classification or the segmentation. So in this case, we can using multiple kernels or filters, right? Each of them will responsible to detect a specific pattern, right? So previously we detect maybe like this edge like oriented in this position. Maybe we have another filter that is detect like a horizontal edge, right? So we, for this second filter, we do the same, right? So we can end up with another, images. So here we call this as a feature map, right? Because, images, basically means this is your original input, but whatever the resulting, we'll call this a feature map, okay? So this is the second filter will result in a second feature map, okay? And, okay, see. Okay, so this is like a animation, right? Just to show, just repeating, right, what we just talked about, right? So how these kernels are moving around across the image and generating a corresponding feature map, right? Okay, so we also have the zero padding. So that's also very common used, because if you don't want to reduce the feature map size, then you can basically do a padding. Then you will get the same size feature map, right? So here we have a 6x6 images. If you do the paddings here, right, you put all the zeros, or you can do some, so this is zero padding. You basically put a 0. But if you like, okay, this maybe introduce some artifacts, you may do some mirroring, right? So you just mirror whatever the first row or first column, just put it here, right? So here we're going to be 1, 1, this is 0, 0, 0, 1. So just do the mirroring. So that's another type of padding. So this is just a simple technique that you can use to maintain so that your feature map maintain the same size. Okay. So that example is very simple, right? Just using a single channel, right? Grayscale image. Of course, most of the time we're dealing with color images, right? It has RGB channels, okay? And even in the medical domain, right? So we may have, or maybe in the remote sensing, you have like hyperspectral, right? You have wavelengths beyond the visible spectrum, RGB, right? You may be near infrared or maybe other wavelengths, right? The hyperspectral image for the remote sensing actually has like hundreds of spectral bands, right? So you resulting image with hundreds of channels, okay? So for this color images, right? So this is basically like a 3D matrix, right? A cube, right? So you have a spatial domain. You also have kind of like a channel domain, right? Red, green, and blue, okay? So to cope with this, right, so because we have 3 channels now, when you specify a filter, you will also have the same channel size, right? So now we have not just a spatial 3x3, we also have a channel size of 3, right? Because our input now is a 3-channel color image, okay? So that's the difference. So if here you have a hyperspectral, like 200 channel sizes, then you will have a filter like 3x3 by 300 or 200 channels. Okay, and you basically do the same, right? So you just do the element-wise multiplication, then summarize the value, right, across all the channels, right? So you result in a single scalar, then will be one value of that feature map. Okay, so that's a basic animation just to show, right, how these 3-channel filters process this 3-channel RGB input. Okay, so here will be an example to exercise, right? So how these dimensions going to be, specified, right? So here we have a input image, right? That could be 32 by 32 as a spatial size, right? Input channel is 3, and the first convolution layer we have the filter or kernel size 5 by 5, which is a spatial size. Then we also have to specify the channel dimension, which is 3, right? Because corresponding to the input, okay? And, if we don't do any of the paddings, then we result in a feature map of spatial size of 28 by 28, okay? And here we have the channel dimension of 6. Why the channel dimension is 6? Yes. So here we have the number of filter or kernel is 6, right? Remember, one filter will result in a one feature map, right? So if we apply 6 different kernels or filters, then we result in 6 feature map, right? So now we have the channel size of this feature map layer is going to be 6, okay? And so the next convolutional layer, then we apply the filter size will be, assuming we have the same spatial size, right? 5 by 5. Now the channel dimension has to go to 6, right? Because we have to operate on this feature map right now, right? And this feature map has 6 channels, okay? And we apply, if we're using 16 different filters or kernels, then we end up with a feature map has 16 channel size, okay? So that's how you can specify or know, based on the channel size or the number of filters you apply, you will know how your feature map size or dimension look like, okay? So far, so good?
How the height and width, the 24 by 24 is calculated? From 28 to 24?
So, yeah, it depends on so there's an equation. So, like, basically based on the height and width and the kernel size, and also the stride you have, right? So I forgot the specific equation here, but you can simply you can easily derive that, right? Because you just put a 5x5 filter. If you have I forgot if the stride is 1 or 2. I think here is probably 1, right? So if you just put this 5x5 here, eventually, right? So 32 divided by 5, right? You have like 6 of them, right? So eventually you may have to. There's only like 2 columns left. Then you cannot fit another. If you don't do the padding, then you cannot fit another kernel on the very right side, right? So then you end up with a reduced size, right? So I forgot there's an equation to derive the specific size. I think you can look at, but I think it's really easy to derive, right? Mathematically, okay. Okay, so this is just like what's the intuition, right, for the convolution, right? So each of these kernels or filters, right? So visually they may look like this, right? So here this is not like 3x3, maybe even larger. So you will see that this kind of filter or kernel trying to detect edges with different orientations, right? So for a specific filter, you will generate a feature map. So based on this feature map, you can see that for this image, some particular edges or orientations has been highlighted, right? Because of the filter is responsible to detect maybe this kind of horizontal or diagonal or vertical edges, right? So this is just a basic illustration, right? How this filter is able to extract those useful information. Of course, as we go to a higher layer, right? So because of the filter or the kernel become more complex, right? So we are not just interested in detecting those very basic edges and corners. We may detect very complex patterns, right? So for the first layer, usually we'll detect very, very basic. Just like if you are familiar with Fourier analysis, right? This can be like DCT transform or some Fourier transforms or wavelet transform, right? Trying to detect specific edges. But as we go to higher layer, right? So you can see we visualize these filters, right? You can see that they have some specific patterns, right? Like the circles, and some of them even contain some color component, right? Because we're dealing with RGB images. As we go even higher layer, right? So we see that there are some complex patterns, right? Some may detect like a human shape, right? So some of them like detect some specific. This I think more look like a tire or car, right? A circular shape, right? So it becomes more and more complex. Okay. And this is an even higher layer, just to visualize that. Okay. Yes.
In the convolution generator, there are some parameters like the kernel size, filter size, also the max pooling if you do the padding, also the stride parameter. There are lots of parameters.
Yes.
To get. So normally when we see a convolution, a standard convolution architecture like dense network or whatever RCMM, you have also provided in the assignment. So this type of network architecture shows the parameter values, like they have set the parameter value on the first convolution layer, second convolution layer. Like how they get those parameters, like they don't mention how they get those parameters. Like they just describe the architecture. I understand the architecture, but is it like they do the experiment, then get the parameters, something like this? Like what is the process of obtaining those parameters?
So yeah, so your question is how we can obtain the parameter number, right, for a specific network. So that basically counting, here we have the convolution, right? Definitely this will be a major part of the parameter, right? Because all these numbers in your convolutional kernels or filters has to be optimized, right? So that's the majority. Also, you have the bias, right? And also some layers have other parameters. So the stride or padding is not a parameter because you don't optimize them, right? You specify this is a stride of 1 and 2, it's a fixed, right? So the pooling layer, you don't have any parameter to optimize. So the parameter we are mentioning there is the parameters you have to optimize, right? Like the poolings, there's no parameter. You just do the specific downsampling, right? Or if you either do the max pool, take the maximum, or you take the average, right? So there's no learnable parameters there. So basically, you can compute by hand, right? So like how many filters you have, what's the filter size, right? And how many filters you use for each of the layer. Then you can manually compute these learnable parameters, right? Then you can sum them up and give a. So right now, for any of the deep learning framework, there's always a function that I forgot which function. Anyone knows which function you can call to compute the parameter size? Anyone knows that? So I don't think you have to do this manually. So people have already written some program, right? So you can just using that to help you to count the number of learnable parameters. Okay, so that's how they. But if you don't know there's no algorithm to help you automatically compute, then of course you can just manually, as I mentioned, right, to count how many learnable parameters you have, then specify that. Yeah. So it's not like every convolutional layer you have different filter size. Usually we have very fixed kind of fixed design, right? So these 3 or these 5 or 10 layers are gonna using 3x3. Usually we only using a spatial size of 3x3, right? So that's a very common and optimized kernel size, right? 3x3 is highly optimized in the CUDA library for acceleration for the matrix multiplication. So usually we have like 3x3 spatial size. That's fixed across all the convolutional layers. So maybe some of the variation is maybe the first 5 layers you're only using 256 kernels or filters, right? And then the next 5 layers you want to increase the channel size or the filter size number, right? You're using 500, right? So basically you can count one layer then multiply by 5. So it's not like you have all these different, the first layer you have 3x3, next layer I'm going to switch to 5x5, and the first layer I'm using 100, the second layer I'm using 200, the next third layer I'm using 400, all these weird number, right? So you kind of have like a very basic design there. So help you to easily compute the number, yeah.
So why do they use a 3x3 filter? Is it because it's RGB or?
No, the 3x3 here basically is the spatial, right? The channel size dimension is going to be always changing, right? Depending on the amount of channels of your previous layer feature map, right? The spatial design of 3x3 is kind of tried and true, right? So, it's efficient, and if you want to using a large kernel, you can do that, but that will have more computation, right? Because we are doing this matrix operation, right? Element-wise multiplication. If you increase to 5x5 or 7x7 or even 10x10, very large kernel, you have more computation, more parameters you have to optimize, right? That's one limitation. Because you have a overly large network, then you have to spend a lot of computation resource to optimize them, right? And another reason is that, you can think about a 5x5 can be approximated by like 2 3x3 in a row, right? Because, a 5x5 is basically you have a more expanded receptive field size, right? So you have a broader or larger context. You look at a 5x5 region. A 3x3 is you only have a smaller region. But if you think about you have the pooling layer. If you reduce the image size, then you can using the next layer. If you're still using the 3x3, and you essentially can also looking at a larger scope, right? Because your image size reduced. A 3x3, you still have in the next layer, you're gonna have a more larger effective filter size, right? So you don't necessarily have to keep, increasing the filter size. Of course, some of the designs they using, like the Inception Net, right? The network, Google Inception Net, they using, multiple kernel sizes, right? I want to using 3x3 and 5x5. This will capture like a multi-scale representation, trying to enrich the feature representation. You can do that, but that comes at the cost of more computation, right? Okay. Okay, so here just show you some of the variants of a convolution operation. So I think this is also related to your question: is why can we using maybe different sizes or more larger sizes, right? So first is the dilated convolution, and we also have this depth-wise separable convolution, and also have the grouped convolution. So we can look at these dilated Chaucer's convolution. Is the idea is they introduce a additional parameter called the dilation rate, right? So here this is a normal 3x3, right? So we look at these 3x3 pixel regions of your input. This dilated convolution is basically, okay, I'm not going to look at these neighboring 3x3 pixel region. So I have a dilation rate, right? So basically I can sample these pixels, right, at a sampling rate interval of 2, right? So, I think this animation tells you, right? So here, the 3x3 pixel is not like adjacent 3x3 pixels, right? So they actually have intervals there, okay? So this gives you the advantage is that I can look at more context, right? So for some of the tasks like segmentation, context is really important, right? So for example, I have a chair, I have a table here, right? So then I have a chair. The boundary is really important, right? So if I only look at this, right, I don't know what's gonna be on this side, right? So maybe there's a lot of missegmentation on the boundary. But if I can look at larger size, right? So maybe I'm not only observe this table, but I'm also able to observe partial of this chair. I know a more general, a larger context, right? So then I can, help the model to decide, okay, this is the boundary of the table and this is the boundary of the chair. So you will see they will, have a better segmentation around the boundary. And another advantage of this kind of using this dilation rate is you are essentially still computing like 9 multiplication, right? Although the field you are looking at is 5 by 5, right? So you look at the size you are looking at is actually 5 by 5, but when you do the multiplication, you only have 9 multiplication, right? Because you are not taking all these 5 by 5 pixels regions, right? You're just taking, like, sample them, right? So I think that's the benefit of these kind of dilated convolution, to maintain the same computation, but at the same time, you're able to increase the receptive field to 5 by 5 in this example, okay? Okay, of course, because you introduce additional control parameter, right, which is the dilation rate, you can increase into like a even larger receptive field, right, by increasing the dilation rate, but you can still maintain the same computation. So this has been shown that, for segmentation tasks, this is really able to help understand a more, context or more global context, right? So this will help segment, especially, object boundaries, right, will be more clear. So for example, this one, they may still have some misclassification of the pixels, right, for some of the boundary. Okay, so I think I missed talk about these two. So this one, this depth-wise separable convolution, I'm not going to expand the discussion here because we have a lecture dedicated to efficient neural network design. I will talk more details there. But here, just to give you a sense, these two are designed to also reduce the computation, okay, as compared to the conventional convolution. So we'll talk about that when we talk about the efficient network design, okay? And there's also a flatten operation. So this is very simple, right? Because after these convolution operation layer and the pooling layer, you end up with these kind of spatial organized feature map, right? So now you can basically, vectorize them, flatten them into a giant, a single vector, right? So then you can basically, try to adding a weights here, trying to encourage more communication, right? So because convolution, you are not connect all the pixels to each other. So flatten, then you can basically do the fully connected layer, right? So you can connect each of the neurons together, okay? So that's the flatten. Then you can connect a couple of fully connected and trying to encourage communication between all these different neuron nodes. And eventually, then you can do the output, okay? And before the generate the output, right, so you also have a specific operation called softmax, right? So basically, if you don't using this softmax, you will end up with produce some of the value that can be unbounded, right? So here we have this, activation multiplied with weight plus the bias, right? That can be any of the value, right? So it can be very large or very small, but it's really difficult for us to interpret, right? So when you say I want to do the classification, then I output a number which is unbounded. Then how can you interpret that, right? What does the 20, 30, 50 mean, right? So we need to come up with some of the value that is interpretable, which for the classification or any of the task, a probability, right, will be easy for us to, interpret, right? So we can, basically the softmax is basically trying to, range or scale these values into the scale of, 0 to 1, right? And they all sum to 1. So in this case, we can using that as a probability for the interpretation, right? So here, maybe I doing the color prediction or classification, right? So I have a green color has a largest probability, maybe 0.5, and the other will be smaller, right? So this is really easy for us to interpret. So that's basically, all these important components put together, right? So we have different layers, and then we have the output, right, in terms of probability, and then then the next question is, once we putting all these pieces together, then how do we optimize them, right? So what is the objective? We're trying to optimize these network so that we eventually end up with these network parameters going to be very good, right, to perform like tasks like classification, detection, or segmentation. So we have to specify the loss function, right? So basically, we'll have, for the supervised training, we'll basically provide the truth label, right? So, this image is a cat, that image is a dog, right? So we have the ground truth label, then we have our output, then you can specify a specific loss function. So there's a number of choices, right? You can think about, what kind of loss functions I want to use, right? So here, if my target is to do like a digit classification, right? So we have 10 digits, and this is the ground truth, right? Ground truth is encoded in a way like a one-hot encoding, right? Because this is a class of 1, right? So this is given the highest probability equal to 100%, right? The other classes, which corresponding to like digits 2, 3, or to 9, it should be assigned as 0, right? Because that's digit 1. So that's our ground truth label. And this is our prediction, right? So this is, again, in terms of probability. And the ideal case is our prediction should be just exactly like your ground truth, right? That means your network can make a very accurate prediction, right? You predict this is 100%, this is a digit 1. But in the initial case, we may not able to achieve this perfect prediction, right? So you may predict, digit 1 maybe 60%. You also have some digit has some certain probability, like 20 or 30%. So you want to optimize this, right? So you can compute the loss. So a simple one is the mean square error, right? So because you have one vector, you have another ground truth vector, so you just do the squared error, right? So here we're trying to minimize this squared error, right? So if you have a prediction which exactly here is 1, the other is 0, then you end up with a loss which is 0, right? That's perfect. That's exactly what I want. But oftentimes you will incur some of the loss, right? Because it's not a perfect prediction. So you can also have this cross entropy loss, right? So you may heard of this. So it's also used a lot. Basically, it's the go-to loss in the classification. So you can using cross entropy as the loss function. So there's also some other loss function. Actually, this is like an open domain, right? So you can always design a better loss function that is able to guide your network optimization, right? Even converge faster or converge to better local minima, right? So so that's the loss function we can specify, we can choose, okay? So once we also clear, right? So what is the objective, right? We want to optimize. So that's defined by the loss function. Then how actually we can optimize, right? How can we reach there, right? So then we have to do the optimization, algorithm. So the commonly used is the gradient descent, right? Not even in the deep learning, right? So if you're doing the logistic regression, you are also using gradient descent, right? You can specify a loss function, then using gradient descent to find these, the optimal location. Right? So this is the gradient descent, right? So the basic idea is you just you have the parameter you want to optimize, right? And you want to compute the the derivative or partial derivative here, and you also have to specify a specific learning rate. So here is alpha, okay? So each time you do a very small update based on the current parameter and also the partial derivative, basically which direction I want to, optimize or change my parameter value, right? So here I just draw a very simple example here, right? So here we have this, loss curve. So if my current, so here's my loss function, j theta, right? So let's look at this point, right? If my current parameter location is here, if we compute the derivative, right? So here is very simple. You basically just look at the slope, okay? So this is a positive value. Alpha, the learning rate is always going to be a positive value, okay? So in this case, the new parameter here is you have the old one minus the learning rate times this derivative, right? So basically, we want to minus something, okay? So minus something, if you look at this, the theta axis, right, we move to the left, okay? So if you look at this, it's actually moving you towards to a local minima, right? So here we can find this is a local minima right here, and this is the right direction you want to move to, okay? You can also have a scenario where you are right here, right? So in this case, this derivative is a negative value, right? Because the slope is negative. So minus alpha, so you basically plus something, right? So that means your parameter is moving to the right direction, okay? But if you look at here, we also have a local minima right here, right? So this is also tells you you are moving to the right direction, okay? So remember, so because this neural network is highly complex, function or mapping function, right? So we are not guaranteed to always go to the best optima. So by doing this, we trying to get, what's the next, or the goal is trying to get the local minima, right? So, but we are not guaranteed to always go to the global minima. So that's other technique, right? So it's also still, a lot of research in this, right? How we are able to find a better local minima so that your network is going to be trained better or generalized better, right? So that's the gradient descent. Then another important component in this network is we also have this nonlinear activation, right? So we have this rectified linear unit ReLU. So that's basically trying to scale your activation, right? Because you are multiply with a weight parameter, right? So we want to scale that. But for this ReLU activation, there's come with the issue, which is the vanishing gradient problem, right? So because if you look at the ReLU, right? So on the left side, so all these will become equals to 0, right? because here we are doing this kind of chain rule, right? Basically, you are multiply, these partial derivative together, right? So because we are layer by layer, node by node, we have to compute the chain rule to compute the gradient. And if you have a very small value, right? Not even zero. If you have a very small value and you multiply a lot of them, you end up with a very small, right, towards zero. Then basically, you are not going to optimize anything, right? Because you end up with a value of 0 times everything is going to be 0, okay? So that's a potential problem. So here, people trying to address the issue is they have some other variants, right? So you have this leaky value or maybe parametric value, right? Trying to have certain slope on the negative side, so you don't, end up with a value of 0, right? When you do the compute the partial derivative, okay? So that's a couple of value or activation functions you can use in your neural network. Okay, so then we've talked about, right? So basically, we are using the gradient descent. One important parameter is the learning rate, right? Because that kind of specifies how much change you want to adapt for each step, right? So what if I choose a big learning rate, right? So what if I use a very small learning rate? What will happen to my optimization, right? So if you use a fairly large learning rate, that means you take a large step, right? Every time during the optimization, then you will, sometime get a very diverged phenomena, which means your network will not able to converge to a local minima, okay? And if you have a very small, right, learning rate, that means, you will have a very slow convergence, okay? So let me just quickly draw something so you get the idea, right? So let's just using a very simple, loss function or landscape, maybe look like this, right? So let's say you are right here, and if you take a big change, right? So maybe a very large learning rate, next step, I'm going here, okay, to this point. And for the next step, I may be shooting over this local minima, right? Because I make a very big change that I end up here, okay? So then the next, if I keeping, optimized, then I actually kind of climb the hill, right? So, or later gradually I come back, I still shooting over this local minima. So you basically kind of doing this kind of back and forth, right? You are not able to exactly land to this local minima, right? So if you have a very large learning rate, okay? But if you have a very small one, the slow convergence is really easy to understand, right? Because every time you take a very small baby step, right? So let's say, unfortunately, your initialization is right here, right? Then you have to take so many steps to converge to this local minima, right? So if you only take a very small step, then you end up with a very slow convergence. You have to train multiple, maybe hundreds training epochs that you are able to reach this local minima, okay? So then the question is, how do we pick this learning rate, right? So what's the rules or what's are the guidelines for us to pick this learning rate? Unfortunately, there's no golden rules, right? So you always follow this rule to pick the learning rate, right? Because there's no one learning rate can rule them all. So, but you can, the basic or good practice is you can start from a high value, right? Because the assumption is that, okay, in your random initialization, you are far away from the local minima, right? So you can take a larger step, right? Just to be bold, right? Take a large step. Let's quickly get close to the local minima. Then we can gradually reduce this learning rate. Maybe you can cut the learning rate by half, right? So we gradually take a small step as we close to the local minima, so we don't end up shooting over, right? So that's the basic idea, right? So you can have a learning rate schedule, right? So the first couple of iterations you can use in a larger learning rate, then gradually you can reduce them, okay? And this is just a couple of a figure just trying to show, right? So if you have a different learning rate, what could happen, right? Your loss curve could be, you're not going down, but you end up going up, right? So this is a very large, high learning rate that you are not able to go to the local minima. And if you have a low learning rate, right, you are going down very slowly, right? So you can see here, you are still not converged, right? So you can keep going, then you can go to this converge point, right? So this good learning rate is you are able to quickly go down, then slowly, right, go to this into this plateau region, okay? All right, so that's some of the guidelines, right? So you can use to choose the proper learning rate, or using some schedule to choose the learning rate. And because of the network is highly complex, right? Because we have a lot of parameters to optimize, we also have to using some, techniques to help regularize the network learning, right? So one is a couple of techniques we use is using the dropout or L2 weight decay, and also using the early stopping, right, to preventing your model trying to overfit, okay? So let's look at some of the techniques here. So here, the first one is the early stopping, right? So the idea is basically you will have a validation set, right? So you have a validation loss. So when during the training, you can evaluate your model at each of the step, right? So you're using this validation set, okay? So once you see, okay, my validation loss or error goes to a certain point, where it's not reducing anymore and become to increase. So this is a good sign to tell you, okay, maybe you should stop, right? Because your model is not able to generalize well, because on the validation loss is going up, right? So this is good stopping point, but you need to have a validation data set to help you to kind of monitoring your training progress, okay? So this is early stopping, right? You don't have to train so many epochs. You can stop right here. Another technique is using the dropout, right? So the dropout means during the training, each of the neurons, right, will have a certain probability to kind of disconnect with the network, right? You can disable these neurons in the network, right? Which means this connection is disabled, right? So the information will not, or the gradient will not pass through these neurons. So why doing that? So I think the research shows that, a lot of neurons, right, if you optimize them together, so there's a phenomenon called co-adaptation, which means all these, a group of neurons maybe behave similarly to achieve a certain goal. This is not what we want, right? Because we want every neurons perform a certain capability, right? Try to recognize different patterns or features so they can collectively together to help improve the recognition capability or generalization capability. So that's why we want to disable some of them, right, to prevent them co-adaptation. So
the reason behind this is kind of like the neurons will go for the more generalization than
yeah, because just like some neuron will tag along, right? So okay, you are good enough, then I will tag along or perform similar things, right? I perform this edge detection, I do the same, and this is not what we want, right? Because we want every neuron to perform some specific capability, when detects or try and go in deeper, uncover some more useful information to help you recognize this is a cat, right? Because for some tasks, it's really difficult, right? If we talk about like fine-grained classification, we have a lot of cat, but we want to, figure out different species, right? Or dog, right? This is Pluto, right? This is German Shepherd, right? This is more difficult, right? Because we have to identify different breed of dogs, not just a general category of dog. So then each one neuron has to try harder to figure out what are the small nuances or small differences, right? But in this case, some of the neurons may not, you can call this like lazy neurons, right? They may not learn something that is very meaningful. So in this case, we intentionally disconnect them, right? So in this case, okay, oh, this neuron is not here, right? So you cannot rely on it. Then you have to come up with something, learn something, right? Trying to predict a very good prediction, right? So that's basically trying to, make the network more generalizable, okay? So, so during the testing, of course, we want to using all of them, right? Because every neuron is trained to extract meaningful information from the data. So we want to using all of them to make the prediction. So the dropout is only applied during the training. Okay. Another way you can think about dropout is, why this is helpful is you can think about this is kind of like a network ensemble, right? During the training, because I'm randomly disable some of the neurons, I end up with a subnetwork like this. I have another subnetwork, 2 and 3, right? So basically, I'm doing this kind of ensemble training, right? So ensemble, you can think of they are different experts, right? So usually, if they are trained well, a set of experts will make more informative or more accurate decision. Okay. So that's some of the technique you can use, right, to regularize your network training. That's from the network training perspective. So we can also, improve the network generalization or training from the data perspective, right? So, so that's the data augmentation comes from. And sometimes, we don't have a lot of training data, right? So especially in medical domain, right? A lot of images are really scarce, right? So some of the disease, right? Some of the scans or patient data is really difficult to obtain, right? So we don't have a lot of data or label data to train, right? So then how to prevent the network overfitting your training data or make it more generalizable, and we can using the data augmentation technique, right? So we can increase the training data. So here are some of the very simple or basic technique you can use, right? So this is basically just image operation. You can do the random cropping, right? Rotation, mirroring, all these things, right? Just to make multiple copies, right? Different copies, not just exactly the same, but different variations of the original input. You can also do color shifting, right? So to change the RGB values to make different copies. Because this is kind of mimic different lighting condition, right? So maybe not all the images taken in under the same illumination or lighting conditions, right? By doing this color shifting or jittering, you are able to simulate a diverse lighting condition, right? To enrich your training data. And this is some results show that this, you can also using color space conversion to make multiple copies, right? So we have RGB. Color space, you can also have HSV, YUV, LAB, different color space to make multiple copies of the data. There's also other technique, right, like a random erasing, right? So you can remove partial of the images, right? Maybe cover this part, right? So cover this portion, randomly erase some part, and to enrich your data. Here, my question is, why this kind of data augmentation is able to help a model to learn better?
It's kind of like increasing more data can give the model to learn more features or different.
But maybe I can think of, okay, if you remove this information, will that basically you lost a lot of detail, or you lost a lot of good information for the network to learn?
But in the real case scenario, there can be an image which has some less information or damaged information. In that case, the model will give more generalized perspective to that part.
Yeah, so the intuition here is that, or a possible justification is that, because we are erasing some of the part, right? Not totally the entire object. Here, I'm covering the ear of the fox, or maybe the eye or the nose, mouth region. This will make this recognize this object more challenging, more difficult, right? So because that information is not there. This actually help the network to learn strong representation, right? If your image, every image is very clear, everything is visible, the network maybe learn some very obvious information, right? So maybe determine this is a fox. I only look at the nose or maybe the ear to determine this is a fox, right? But some other very good characteristics, maybe the color, the patterns, also help determine this is a specific object, right? So if we remove that, if we can come up with some of the random erasing, right, we may, remove some of the obvious information there. So the network has to try harder to figure out, okay, without this information, what other patterns I have to look into to make an accurate decision? This is a fox, right? So this basically helps the network learn stronger representation when during the testing, right? So maybe not all the fox oriented in this direction, right? They have some different data distributions that can help the network generalize better, okay? And here we can even using some of the apply not just a single operations to change data, right? We can apply a sort of operations in a sequence, right? So here, this paper specifically studied like what kind of augmentation policy we can use to achieve the best augmented data to help the model learn, right? So here they have some basic operations, rotation, translation, inverting, polarizing, contrast enhancement, right? So they're using reinforcement learning technique trying to figure out, right, what is the best strategy, apply these operations so I can achieve the augmented data that is able to help the model to learn, okay? There's also some other technique, right? The cut mix is also used a lot. So basically you cut out some part and you mix it or you fill this blank with some other images, right? So this example is basically like a cat and dog mixture, right? So you have a dog with 60% of probability, and you have a cat with 40% of probability, right? So this also makes the, task more challenging, right? So I have to, based on this information, to determine there's a 60% chance this is a dog, but I also have to rely on this information to determine, right, there's also a cat exists in this data, right? So there's more on these data augmentation. So if you are interested, I list these information here. So you can take a look at that, okay? And also there's some reading materials. So if you are not familiar with convolutional neural network, or you have never trained a deep neural network, so these are very good or very basic examples that to help you to go through a specific example, right? Do the digit classification, maybe do some simple like CFAR10 image classification. So you can take a look at that, okay? Also, this is a deep learning tuning playbook. So give you step by step. You can also take the read. If you're interested, you can read that as well. Okay. So then next, I will quickly go through some of the basic or the common network architectures, right? Or maybe you are already familiar with, right? So the AlexNet, right? So the first very successful deep neural network that is outperforms other methods in a significant margin on ImageNet. I think ImageNet Challenge 2012, right? So come from Jeff Hinton's group. So the AlexNet, right? So basically have conv layers, pooling, very basic, fully connected, right? Not a lot of fancy stuff, all these, but make it deeper. So that is able to run on the commercial GPU and is able to achieve very good performance. Next, we'll have this VGG, right? VGG network that has some specific design and more deeper, right? Which is better performance than AlexNet. And this inception network, which has, have this inception module, will have using multiple convolutional size, right? Not just 3x3, You can using 5x5, 1x1, different kernel sizes, and trying to capture multi-scale representation. And of course, the modern or most famous one, right? People still widely used is the ResNet, right? So basically, introduce this skip connection, right? Skip connection that is able to help in the back propagation. When you have a very deep neural network, right? So the skip connection is still enable, the network to still train better. Okay. So I think for now, like AnixNet, GoogleNet, VGG, probably not a lot. Well, you're still using that. Usually, like the ResNet is if you still want to using CN, right? The ResNet is still the go-to network, right? So they have different versions, right? Depending on the network depth, right? So you have a ResNet 18, which is a smaller one, right? Less than 20 layers, right? So you have ResNet 50, right? You can think of this as a intermediate size network, right? Of course, you have a larger size ResNet 101, or even larger or more layers. So that has more parameter size, right? Depending on your application and your resources you have, then you can choose whatever the network you want. So as I mentioned in the programming assignment 1, right? So you will do the classification. Considering all these computation resources, you can choose like a smaller network, like the ResNet 18, as the backbone choice if you want to do some simple classification task. Okay. Okay, so here are some of if you're using PyTorch, right? So all these very popular ones doing the classification, all these networks. Structures are readily available, right? So they also have pre-trained on the ImageNet, so you can easily load these pre-trained weights. So maybe to do some simple fine-tuning on the downstream task, okay? If you're using Keras, they also have a similar thing, right? You have different models, different architectures that you can use, okay? So they also specify the model size, right? So basically, you can, based on like what is your GPU, right? So if your GPU does not have a lot of memory, then you have to figure out, right, what kind of model size I can afford, right? So you may only afford a smaller model with less than 100 millions of parameter. Okay. Okay, so I think we don't have much time, so I'm gonna stop here. I think I can talk about this in the next class, right? Some of the interpretability of the deep neural network. So before we end, I think there's some question here. Let me see. You can see this. Model summary. Okay, shouldn't we always target to achieve global minima? Yes, that's always the goal, but you don't always get what you wish, right? So because there's so many local minimas, then you sometimes stuck there, right? So of course there's some technique, right? You can, when you go to a local minima, then you can increase the learning rate to jump out of it, right? Try to redo this again. Maybe hopefully you can go to a better local minima, but it's not guaranteed. But this is always the goal. But reality is you don't always end up with the global minima. Okay. Okay. Any questions? Okay. All right. So yeah, I know this is a really quick introduction, but unfortunately we don't have much time to spend like a dedicated couple of lectures to talk about these details. So I have to run very quickly to give you a very brief overview. Of course, some of you guys are already familiar with this, but hopefully this will also kind of strengthen some of the knowledge you have before. Okay. Okay. All right. Thank you, guys. I'll see you next week. Everyone has a nice weekend. Okay. All right.